with Laura García-Álvarez, Fermion-fermion scattering through superconducting circuits.
Okay, thank you. First of all, I would like to thank the organizers for giving me this opportunity to present my recent work in Fermion-fermion scattering with superconducting circuits. For those of you who don't know me, I am Laura García-Álvarez, and I work in the University of the Basque country in Spain. And I will present here some recent work we have been developing in order to solve some quantum field theory problems with quantum simulation. This is QS Group. I belong to that group, led by Professor Enrique Solano. And my lines of research are quantum optics, quantum information, quantum field theories, superconducting circuits. So I will present you this work. This is the outline I am going to follow. First, I will tell you some basics about quantum field theory and why it is difficult to compute quantities of quantum field theory. And then I will explain you how quantum simulations can help us to compute that quantities. We have a novel idea involving digital and analog quantum simulations, and I will compare it to current proposals, and I will show you how this boosts the efficiency of the computations. And later I will enter into the details, presenting the quantum field theory model that we have proposed, just a proof of principle model, and in the details of the superconducting circuit device we are considering for the realization. And in the end, I will sum up with some ideas, some drawbacks, some ideas of the proposal. So first, some basics of quantum field theories. For those who are not familiar with this field, quantum field theory is among the deepest description of nature. It reconciles quantum mechanics and special relativity. To do that, you have to think in quantum mechanics and in special relativity. In quantum mechanics, space is an eigenvalue of an operator. And in special relativity, space is at the same level at that time. Time in quantum mechanics is a parameter, and here both are parameters. So how can you mix those fields in order to create this quantum field theory? What you do is to define a set of operators, this CXT. This is called quantum field, and this has different values at each point of the space-time. This is why quantum field theory is said to have infinite degrees of freedom. This is what makes quantum field theory so difficult. These quantum fields are the quantum description of classical fields. For example, the electromagnetic field. You can describe it with quantum field theory, and it takes into account the photons, the quantum mechanical aspects. This theory can describe a phenomenon where the number of particles change over time. So this is why it is so important, and why it describes some phenomena that quantum mechanics can. Computations of quantum field theory rely on perturbation theory, basically, and what you do is to expand the evolution operators in this series in terms of the coupling strength. And what you compute is up to certain powers of the coupling, the quantities. You also can use classical numerical simulations such as lattice gauge theories, density matrix normalization group, matrix states, other kind of simulations. In this one, what you do is to discretize in a lattice the space and the time, to assign a value at each point to the field, compute the quantities, and then extrapolate to the spacing of the lattice A going to 0. That way you can compute some quantities, other not, but this is how people are currently solving the problems of quantum field theory. What happens in some regimes, these perturbative methods, the Feynman diagrams, the perturbation expansion, is non-reliable. So you have to trust only in classical numerical simulation, lattice gauge theories, TMRG and PS, as I told you. But these numerical classical simulations are computationally fast. The time of computing grows exponentially with the size of the system. So we have to think in other ways of computing. Here it's where quantum simulations can help. And up to now, there are. Yes.
Sorry, I just wanted to clarify. What do you mean when you say that the perturbative methods are become unreliable? Do you mean that the loop effects get large?
Yeah, what I mean is that there are some phase transitions or there are some regimes where the number of Feynman diagrams that you have to compute grows exponentially, and you have to compute a lot of diagrams, or even if you compute those diagrams, maybe you are in a quantum phase regime that this is not reliable. That is what I mean. Okay, how quantum simulations can help in this sense. Also, the computationally problem is hard because the time grows exponentially. So up to now, there are two kinds of proposals. I divided it in two types. The first one is based on lattice-gate theories. For example, in this paper, they developed a way of encoding quantum fields in qubits, and they developed the algorithm to initialize the states, to compute quantities. But for me, the problem with these proposals is that they are not, they need of millions of qubits to extract quantities of them. You need to achieve a high number of controllable qubits, millions, in order to compute quantities. The other kind of proposals are these quantum simulations. They start in other way. Instead of considering that infinite number of degrees of freedom, they start from a discrete number of degrees of freedom, and then they propose how to scale it up. This you can do in trapped ions, for example, but you need to scale it up in order to achieve full-fledged quantum field theory, because quantum field theory has an infinite number of degrees of freedom. So we thought of this quantum simulation, and these are the characteristics. No? This is a digital quantum simulation. You have to expand the evolution operator in several factors, and this is an approximation of the evolution. They consider discrete number of fermionic modes, not an infinite, not a continuum, and they consider also a discrete number of bosonic modes. The fermionic modes are encoded in the levels of the qubits of the trapped ions, and the bosonic modes in the vibrational modes of the chain, in the normal modes. That way, they propose how to scale it up in order to compute quantities of quantum field theory. But as I told you, this is not full-fledged quantum field theory because you deal with a discrete number of degrees of freedom. So we think in superconducting circuits, and what is the difference between trapped ions and superconducting circuits? How can we profit from that quantum platform? So at this point, you will not understand this slide. I will arrive later to this. But we think, okay, in superconducting circuits, we have these open transmission lines. So here, we think we have a continuum of bosonic modes. We don't need to discretize the bosonic modes. So let's profit from that. The fermionic modes, you don't have this continuum in superconducting circuits, but you can encode it in qubits. So we encode the fermions here in the qubits. In the models, probably you need to perform multi-qubit gates. How? Maybe through a cavity, maybe you have other methods to perform these multi-qubit gates. And also maybe the bosonic part needs to evolve freely, not coupled to the fermions. So this is why we thought in an ancilla qubit or a driving or other way of computing. That is the difference between trapped ions and superconducting circuits. This continuum of bosonic modes that appear in the transmission line. So let's profit from that. I start with the general scheme now of the proposal. We propose a digital quantum simulation because to construct the right Hamiltonian is difficult. And we expand the evolution operator in these factors, in several Trotter steps for different parts of the Hamiltonian. So still we are in a digital quantum simulation. We still deal with discrete fermionic modes, and we map these fermionic modes via the Jordan-Wigner transformation into qubits. This is a non-local mapping. You map a fermion in, for example, in this proposal in 2 qubits. This is non-local. But you can encode the information of the fermions in the qubits. And this is the novelty, the new thing that boosts the efficiency. We have the continuum of bosonic modes in the open line. So that way, we boost the efficiency of the simulation. We don't need to scale the number of bosonic modes as in trapped ions. We have it. So this is the analog part of the simulation. That is why it is called digital analog quantum simulation. Let's see how can we do that. So this is the quantum field theory model. We proposed a basic quantum field theory model just to try to implement this continuum and how to compute quantities from this. So we propose this Fermion interaction model. These are the free energies of the fermions and antifermions, the free energy of the bosons. This is the fermionic field, and this is the bosonic field. This interaction terms describes interaction of fermions mediated by a bosonic field. This is the bosonic field. These are the expression of the fields. As you see, you can expand the bosonic field in terms of these creation and annihilation operators. As in the transmission line, it is the same. And the fermionic field is like this. You have these creation and annihilation fermionic operators with this commutation relation. You have to encode it to be able to encode it via the Jordan-Wigner transformation in the qubits. What are the processes that this simple model can describe? Fermion self-interaction, per-creation and annihilation of fermions. As I told you, quantum field theories deals with phenomena that have a variable number of particles, and also scattering, of course, scattering of fermions mediated by a bosonic field. So first, we have to discretize these fermionic modes because in superconducting circuits you don't have that. How? Let's think cleverly, and we thought about these co-moving modes. You can discretize it, you can choose the basis you want. So here we choose this basis of creation and annihilation operators. Each of these operators creates a wave packet. You can define it like that, a traveling wave packet, and that way we are able to describe scattering in a most efficient way. Instead of plain waves, we consider just certain wave packets of fermions. When you discretize in this basis, you have to think in the Hamiltonian and how it is now expressed. So this is the fermionic field now, and these coefficients are computed like this, in terms of the shape of the packets that you are considering. This is just the anti-commutator. We deal, as I said, with a discrete fermionic modes, but also a finite number of fermionic modes. The number of fermionic modes depends on the number of qubits that you have in your setup. Here we have considered 2 qubits, but I'll tell you how to scale it up. But since we consider 2 qubits, we expand it into operators. Now, after all these approximations, these mappings, these discretizations, how the interaction Hamiltonian that I showed you before looks like this. This is the Jordan-Wigner mapping for 2 fermions. So we have to rewrite everything, and this is the Hamiltonian that we have in the end. We have to be able to do the evolution of that in the superconducting device. So we look at the interaction terms that appear, and we have this bosonic part, this continuum that is in the transmission line, coupled to this identity. This is the part that we will do with the ancilla. This is the free evolution of the bosonic part. This is the continuum of bosons coupled to these single qubit gates. We have to figure out how to do that. And also this bosonic part coupled to these 2 qubit gates. So we have 3 kinds of interaction in the Hamiltonian model. We have this, which is the free evolution of the bosons. This, which is the bosons, the continuum of bosons coupled to the single qubit gates, and this continuum coupled to these 2 qubit gates. How to do each of them? We will, as I told you, this is a digital simulation. digital analog. Digital in the sense that we have to consider each of these kinds of interaction, and analog in the sense that we are introducing the continuum of boson. We are not discretizing, we are not encoding this in other ways. We have it analogically. So what do we need to perform this digital simulation? We need tunable coupling qubits with cavities and open transmission lines. Why? Because we need to be able in each further step to switch on and off the coupling with the transmission line, with the bosons. With cavities, why? Because we need to be able to perform these multi-qubit gates, these Molnar-Sorensen gates. So in the previous slide, I showed you that we can do that through a cavity, but maybe there are other ways. But if we use a cavity, we need to be able to couple and decouple the qubit with the cavities. What we need also, the open transmission line with a finite bandwidth or a back cavity or some device that had a profile of modes, of several modes, of a continuum of modes. What are the targets? The switching between the qubit operations and the coupling to the open line, because we need that because we are in a digital quantum simulation. We need the qubits to implement the discretized fermionic modes, and we need the open transmission line to simulate the continuum of bosonic modes, which is the novel thing here. So again, this maybe you are able to understand more here. This is the proof of principle proposal. We encode here the bosons, here the fermions in the qubits via the Jordan-Wigner transformation. We need to rewrite the Hamiltonian, but you have seen it. This ancilla qubit is used to simulate the free evolution of the bosonic part. And this cavity allows us to perform multi-qubit gates between these two qubits. That way, we'll be able to simulate the previous Hamiltonian, which is a Hamiltonian of quantum field theory. This is one of the qubits that we consider that you can use any qubit that is tunable and switchable with cavities with transmission lines. This is a proposal of how, but you can use other qubits. Here you see that manipulating the magnetic flux, you are able to here manipulate the frequency of the qubits and also the coupling with the cavity and with the transmission line. You can switch on and off. We need a tunable coupling qubit with cavities and with transmission lines. That is one of those qubits, but I think there are more. So the only thing is to be switchable and tunable. How to perform the interaction, the two qubit gate plus the continuum, plus the evolution of the continuum. This is the scheme of gates. Here we perform a Molnar-Sorensen gate, then a single gate. Here you couple with the continuum in order to include that in the unitary evolution, and then an inverse Molnar-Sorensen gate. That way you can achieve this kind of evolution. And as you remember, we have these two qubit gates coupled to the continuum. This is the scheme of the simulation of that gates. This ancilla qubit is used to simulate the free evolution of the Hamiltonian. It was a continuum times a unit times a unit. This is what allows us to simulate that. And the single qubit rotation, just coupled to the continuum, you perform the rotations. So we are able to perform every kind of interaction that appears in the previous Hamiltonian. This Molnar-Sorensen gate implementation, I put this reference because maybe you know this gate for trapped ions, but for superconducting circuits, this is a new proposal of how to simulate that in the previous qubit. This is new. This is because in principle, if you scale it up, you need a Molnar-Sorensen gate between all of the qubits. This is a multi-qubit gate. So let's remember, this is the Hamiltonian of the setup. You have this, a coupling with the continuum, tunable with these external fluxes, and this is a coupling with the cavity. This allows us to to perform the Molmer-Sørensen gate. This is the mode of the resonator, and these are the continuum of modes of the transmission mode. As you notice, we have this integral on K because it appears in the transmission line. But how to simulate that integral on X? So the way of doing it is to consider these quantities. This integral is a number, so we can include it in the coupling strength of the qubits with the transmission line. We'll need to be able to compute this quantity, which is a number, this is an integral, and then this can enter onto the coupling of the qubit with the transmission line. That way we are able to deal with this integral on X. It is also a continuum, but just a number after you integrate. In the end, this how to extract information, what quantities can you measure, what are the fermionic states. You have to go to this dictionary, this Jordan-Wigner mapping, and see, okay, my fermion is the state that creates this operator. So let's see what is the vacuum, the state with one fermion, with one anti-fermion. I use this mapping. These are the operators in terms of the spin operators, and then I apply to states of the qubits. And I realize that the vacuum is this state because this is annihilated by this, that the state with one fermion is this, and with one anti-fermion is this. So if I measure the qubits and see up and down, I see, okay, I'm in the state with one fermion. If I measure this is the state of one anti-fermion. This, you extract information with this mapping, with this dictionary. You say, okay, you have the continuum of bosonic modes, but the fermions are still discrete, are still finite, okay, but you can scale it up and consider many wave packets, and maybe scattering between those wave packets of fermions, just putting more qubits here. You have to keep only one ancilla, because the free evolution part you can do it only with one. And here are encoded the information of more fermionic modes, more fermions. You need a cavity, following that proposal of Molmer-Sørensen gate, you need a cavity relating all of those fermions. But if you are able to perform the Molmer-Sørensen gate in other way, you can maybe get rid of the cavity. This is open field. The Jordan-Wigner mapping now is a bit strange because you map one fermion in all of the qubits. So you have to identify analogously as in the previous slide the state of one fermion in all the qubits. The state with zero, the vacuum in all the qubits. The state of whatever in all the qubits. This is a non-local mapping. So you have to read in the end all the qubits. What can you measure in this simulation? Okay, if we are able to identify the state of fermions, anti-fermions, you can start with a state with one fermion, then let the system evolve, and measure if it ends in the same state. This is called Fermion Self-Interaction. If you start in a state of one fermion and anti-fermion and you end in the vacuum, this is the pair annihilation. If you start with the vacuum and end with the state with fermion and anti-fermion, this is the pair creation. If you want to measure scattering events, you will need more qubits, more fermions, and for example, start with one wave packet with for the fermion, one for the anti-fermion, and see in which wave packets you end. So you can start with K prime and end with P prime. You have to add more qubits to measure these scattering events. But in principle, the only thing that you need is this dictionary, this Jordan-Wigner mapping, how to identify the state of the fermions, and then extract the information. See this, measure these quantities. me, the experimental challenges, because this is a novel idea, and this is the first proposal involving the continuum. One of them is these multi-qubit gates with superconducting circuits. You need to perform, if you scale the system up, you need to perform a multi-qubit gate between, for example, 4 qubits, n qubits. Also, these tunable and switchable couplings with of the qubit with the transmission line and with the cavities. How to switch on and off a qubit, the coupling of the qubit with a cavity and with a transmission line, which has several modes. How to perform this switch off. And this is to end. This is just a pictorial way of saying things. No? This is the setup, just an artistic picture, and these are the previous Feynman diagrams of all of the perturbation series. Here we have, if you think, we have non-perturbative results in the sense that we are simulating the complete unitary evolution operator. We have all the Feynman diagrams involving 2 fermions in this case. We have all of them. The cutting is completely different. You don't cut at certain powers of the coupling strength. You have the complete unitary operator. Where is the cutoff? The cutoff is in the discrete number of fermions and in the finite number of fermions. But it is completely different. A completely different approach that also needs some theoretical development in how this fits in the quantities, how you are cutting the space in other ways. So you have to think how this affects your quantities. But in principle, all the Feynman diagrams are there in the unitary operator. To sum up, we have proposed a quantum simulation of Fermion-fermion interaction in a circuit QED setup. We have discretized the fermionic modes because we don't have these fermionic modes in the superconducting devices. We have mapped them into qubits via the multidimensional Jordan-Wigner transformation. This is the dictionary I told you. We use, this is the novelty, the transmission line, the open transmission line to simulate the bosonic continuum of quantum field theories. This boosts the efficiency. This is the analog part of the simulation. Since we have all of this, we have to develop novel methods involving digital and analog simulation and multi-qubit gates because we have to write the Hamiltonian, see what are the terms, see how to simulate them. So we have to think in how to do it in an efficient way via this Molmer-Sørensen gate. And the next step, you have seen, we have started in trapped ions in discrete fermionic modes and finite fermionic modes, but also discrete bosonic modes and finite bosonic modes. We have jumped from these discrete bosonic modes to a continuum of bosonic modes, and the next theoretical challenge is how to simulate this continuum of fermionic modes. If we achieve that, we are in a full-fledged simulation of quantum field theories. We do not need a high number of controllable qubits. We have the tools in the current setup. And thank you for your attention.
I've got a question with use of the Molmer-Sørensen gate. Computer scientists often criticize such gates because of the fact that they enact a fan-out, which is known to allow some pretty powerful computational properties. So I was just kind of wondering if you could comment about the viability of scaling up the Molmer-Sørensen gate to really large systems, if any experimental challenges.
You mean how to perform that Molmer-Sørensen gate?
For say hundreds of qubits.
Yeah. That is related to this reference I put here. It would be done through a cavity coupling all the qubits, but this is just a theoretical proposal. You can also divide this Molmer-Sørensen gate into qubit gates, but the number of gates required is high. So if you can compute in one single state this Molmer-Sørensen gate with this proposal, you are efficient. If not, the number
Yeah, I
of
guess the essence of my question really was, when can we do this in one step? And is this going to be harder as you make the system?
I think in trapped ions it was done with 4 qubits.
Yeah.
And as Rami said, you can decompose them into qubit gates, and the number of gates scales up linearly.
Yeah.
So this is not such a huge.
Yeah. This is also an experimental challenge between.
Usually with the cavity depends on how many qubits you can couple to, and also the cavity depends on the specific setup. Of course, perhaps it's not 100, it could be like 10.
What is the logic that you're trying to do with the Moller-Sorensen gate?
The logic is that this gate allows us to do this kind of interaction.
So it's a sigma z, sigma x, or oh, okay.
This is the Moller-Sorensen, and this is the sum of all of them.
So
If you are able to do this kind of interaction other way, you are in, because this is the interaction that appears in the Hamiltonian. So how we figure out how to do that is with this Moller-Sorensen. You need this coupled to the continuum. The continuum enter in these single qubit gates.
so so you've given an example of doing this with this, but can you produce the net interaction you need with other kind of gates?
Yeah, you have to think in a way of producing this kind of interaction involving the continuum. So the continuum here enters here.
Yeah,
But
because
if you're able to think in other way, but what you need is just this.
You can reduce to 2 qubit gates, John. No problem.
Yeah. The problem is the scale now.
Yeah, for n-fermionic modes, you need n to
I understand.
nodes, but 1 moment, 2 moments, and it's not that different. The number of gates you need for n-fermionic modes is constant. The number of moments
I understand. Okay, great.
but it grows linearly in the number of qubit gates.
So you can forget about the Moller-Sorensen and just do any contour nodes.
Okay.
So I have a question on you use the open transmission line to basically simulate the continuum bosonic modes. But in this case, the open transmission line coupled to any of your systems, the spectrum is known, right? Because open transmission line, you can immediately write down basically how the mode is actually, how the continuous mode is going to couple. Basically, you know the coupling coefficient from open transmission line. So I'm wondering if you can actually have basically what type of bosonic bus you want in the simulation, and also can you actually engineer how the bus couple to your system?
Yes, you mean the coupling with the continuum? How is the
Because
coupling?
open transmission line is a system that it basically knows the property. Basically, you write down this as a bus. You write down basically the bus spectral density. You know what it is, right?
Yeah.
My question is, can you actually engineer this?
Yeah, you can consider an open transmission line aligned with a 50 ohm in the end, even if it is dissipative, because you are simulating processes that maybe are dissipative also in the real world. And you can consider a back cavity. You just need to couple with a high density of modes. That is a boost in front of other proposals. You need just a coupling, not with a single mode, but with a profile. If the modes are near, you couple with all of them. So you are beyond the other proposals in that case. Okay, there is a cutoff in the mode, but you can couple the system with all the profile modes. The modes are near in the frequency.
So one issue that I may be concerned about from the field theory side is that oftentimes Hamiltonian descriptions of field theories, particularly relativistic field theories, are difficult to write down.
Yeah.
And so, in particular, it's not clear to me how this setup deals with relativistic loop effects.
With relativistic effect.
Loop effects, where if I understand correctly, you have a freely propagating bosonic mode along transmission line, which basically, in some sense, spells out a specific direction of time as a special variable in the Hamiltonian formalism. It's related to, because the boson will propagate just with the time coordinate. But for relativistic field theory, oftentimes you can't specify time as a special coordinate that's different from the spatial coordinates. So I was wondering if you could comment on how you
We have not considered that. We consider the bosonic part as a bar, as an environment of of the interactions. So we have the fermions coupled to this continuum, but we do not engineer any bosons in that transmission line. We consider that as an environment of bosons. And you couple this fermionic field through this bosonic field, but we consider this as a bad. We are not engineering nothing that we can do. Yes.
So if you comment on how you're sure that your method matches onto relativistic.
Onto relativistic.
Why it shouldn't, if it is covariant?
Yeah, I mean,
I don't see it.
If you write a covariant Hamiltonian,
For example, if you put there as
We simulate a simplified model of QED and we compute
Yes.
the Hamiltonian with the dynamic transformation from the dynamics. This is what we can do.
you can match it to your result.
I mean, this is a simplified model. You
Yeah, this
cannot
is-
solve the QED with this model at the level of precision that you solve in the collider. There is a way to define a theory that couples primary modes to bosonic modes, in which you have continuous bosonic modes that
Yeah.
will discover.
Yeah, if the problem is with the model, this model we have proposed it just the simplest we can think of to involve the continuum. But as you see, this describes only scalar bosons and fermions, and this relativistic part is in the transformation, in the Lorentz. If it is covariant, we are simulating covariant Hamiltonian. Even if your system is not relativistic.
You will get a Hamiltonian, and then if you simplify that Hamiltonian, you will get something. But of course, it's a simplified model.
But we can
okay, thank you. So Phillip Stancil is going to talk next on molecular collisions on classical and quantum computers.
So I'm Phillip Stancil, also from the University of Georgia. I'm probably the only person here who doesn't do quantum computing. So actually, we do molecular collisions, mostly on classical computers. But for the last, 8 years or so, Mike Bell and I have been, Andrew Zorberg have been discussing, are there any kind of interesting problems in collisions that could be done on quantum computers? And so my goal today is first to know that you need to know what can you do on a classical computer, collision problems. What's the status today? And then where is there some opportunity to use quantum computers to fill the gap? Okay. So where's that one? Yeah. Okay. So to have to make a distinction, when we think about quantum chemistry, there's lots of activity on quantum computers for quantum chemistry, but that's calculating the electronic structure, okay, potential energy curves, potential energy surfaces. Distinguish that from dynamics, which is some collisional process. There hasn't been much activity, at least I'm aware of, to doing chemical dynamics on quantum computers. Probably the first paper I'm aware of is this one by Lidar and Wong, in which they looked at proposals to calculate thermal rates. And just to clarify what a thermal rate is from chemistry, it is, say, a cross-section, which I'll find a little bit later, averaged over some Maxwellian distribution of velocities, and then averaged again over some Boltzmann distribution of internal states of the colliders. So some highly average, say, maybe at room temperature. Okay. And so they gave a proposal in this paper. A little bit later, the group of Alain Asperou looked at a way to calculate a similar property, but using gauge-based approach, called digital quantum simulation. And there's even been a proposal from Franco Nori's group of how to use quantum dots to at least emulate typical molecular reactors. processes. And the standard one for quantum chemistry, quantum dynamics is just HH2 reactive scattering. And there may be a few others, but it's pretty sparse. The Mike Geller's group, in the last few years, came with an idea which they call a single excitation subspace approach to look at quantum collisional problems. However, this approach I'll discuss towards the end. There are no gates, there are no trotter steps. It's really just a general purpose, time-dependent Schrödinger equation solver. Done in one shot. Okay, so I'll get that towards the end. Okay, so I'm going to give you some quick little primer on potentials that are used in scattering calculations, scattering methods, and then I'll look at a couple cases, one very large scattering problem, and then kind of a simple one, which we suppose could be used to test how well we could do this on a quantum computer. And then I'll look at proposal to look at a collision problem with the SES method. Okay, so briefly, we're funded by NASA, because most of our collision work is actually done for astrophysical applications. We have a little bit of NSF money. And so over here on the side of the group of people that have been involved in the work on the atomic collision side, mostly done by my research associate, Ben Yang, and also my former grad student, Zhiren Yin. And on the right side are those people involved in thinking about how to do these collisional problems on a quantum computer. And some of the work I'll show was done by Mike's former student, Emily Frederick. Okay. So how we do collisional problems, and most chemical physics community does, is in a two-step approach. First, we have potential energy surface, which we'll assume we can calculate with quantum mechanics methods on a classical computer. There's huge literature on how to do it. Okay, and I say there's no problem there how to do that. So once we have this potential surface, it's a hard problem, but can be done. Then we take that and we go on and do nuclear dynamics, the scattering of the heavy particles on this surface. And there's a variety of approaches, which I'll come to a little bit later. I've got a couple more slides of how to do this, but there's lots of theoretical approaches. Okay, so we have this two step, and today I want to focus on this, assuming we have that. Okay. There's other approaches which can be done on a quantum computer or a classical computer, which bypasses the need to calculate the potential surface. Just tracking the motion of all the particles. Okay, I won't discuss that at all today. Okay. So the first thing to assume is we have a separation of the electronic from the nuclear motion. It's called the Born-Oppenheimer approximation, right? And so that's the assumption we'll make. And so we have a potential energy surface, which we can obtain on a classical computer, E. And then the size of this potential, in terms of spatial dimensions, grows the number of atoms. And for greater than 2 atoms, it grows like 3 times the number of atoms minus 6. It doesn't work for 2 atoms, that equation. But for anything else, it works. Okay. And so here's just a typical example, collision of, say, hydrogen on CO, 3-atom system. And we have a coordinate from the colliding H to the nuclear center of mass of the CO, capital R, and then there's a bond length and then an angle. So three coordinates. Right? So for ion diatom collision, it's a 3-dimensional surface. Right? If you go to 4 atoms, 2 diatomic collisions, it's 6-dimensional. Okay? 2 atoms is only 1-dimensional. Okay, so these surfaces can be, as long as my atoms are not too heavy, titanium or iron something, can be calculated relatively straightforward. Okay, so just to make sure all on the same page, what is a cross-section? The thing we mostly calculate. Okay, so just imagine we have some particle C with some spatial dimension rho, maybe over the wave function, and we send in another particle B to collide with it. We start with some impact parameter, okay, away from Z, and B comes in and interacts with C and scatters. Okay, so this is a semi-classical description. Okay. And so what we want to know is the probability for some sort of interaction, say some change in internal states, which is measured over here at some infinite time. And then once we get that probability, we can compute a cross-section by just integrating over the probability times the impact parameter. And so just to get a feeling for the magnitude, classically, it's just pi times, it's just to project the area of the target. So for atomic molecular collisions, angstrom squared, we're looking at. Okay. So that's the cross section. And we'll discuss this probability a little bit later. Okay. So what kind of interesting processes might we look at? Say we have a collision of two diatomic species. Okay. And V and J are the vibrational rotational quantum numbers. And it could collide with another diatomic, and it could have a change of state only. So that's an inelastic process. We had changes of internal states inelastic. You can also have some sort of reactive process in which the reactants and the products are different. Okay. They can also have changes of state. You can also have dissociation of one of the colliders. Okay. And if one of these was an ion, we could have a swapping of the charge. All those could generally be classified as reactive. Due to some time limits today, I'm just going to focus on the inelastic type collisions, okay, and illustrate these processes. And over here is just to kind of give you a feel for the scale. If we change electronic states, what are the orders of magnitude? So a few eV for electronic excitations. And also we use this unit wave numbers. So one wave number is about 10,000 wave numbers is about 1 eV. Okay. So that's electronic state. We can also have way down to changes in just hyperfine states. Okay, that's on the order of micro eV. Today I'll focus this on the electronic and vibrational type transitions. Okay, so to understand how this is done, this list here the most common methods that are used. Of course, there are many other methods that are used in classical computing, but these are the most common. Generally going down to the bottom in terms of accuracy, higher accuracy at the top, which means also in terms of computing time going up this way. Okay. And so the very first method, which is the method we most use in my group, we solve the time-independent Schrödinger equation. It's a fully quantum approach. It's valid roughly at any energy, from nanokelvin to tens of keV, but it becomes a little intractable, really high energy. But it could be done. Okay. And in this method, we use what's called the closed coupling approach, which I'll discuss next. And we also have molecular orbitals of the colliding species. So it's often written as QMOCC. Okay. All the rest of the methods are time-dependent approaches. Okay, so first one is the time-dependent Schrödinger equation, which could use molecular orbitals. Okay. Now, and over here is roughly the range of energies that these methods are thought to be valid. Okay, as soon as I introduce some time dependence, I'm really doing a semi-classical approach. Right? So the heavy particles actually describe classically their motion. So the electrons were described quantum mechanically in the potential energy surface. Okay. What's really popular today in the quantum chemistry, quantum dynamics method group or field is instead time-dependent wave packet propagation. That potential surface, instead of a Gaussian wave packet, launch it, and then look sometime later at what happened to it, project it out. Okay? Very popular approach, but it does have some limitations of what energy range is valid. You can even go to the extreme and just solve Newton's equations. It's very popular too. Also, chemical physics community because it's very simple. It runs really fast. Okay, but it has some limitations on the accuracy. Okay, so as I mentioned, all of these methods we have to specify some sort of trajectories, classical, and this one is the most accurate one most used in my group, but we'll today focus on. I'll discuss both of these. It turns out that this method, the semi-classical molecular orbital closed coupling, maps perfectly to the single excitation subspace approach on a quantum computer. Okay. So let me just try to avoid some jargon, but explain to you what does closed coupling mean and what are channels. Okay. So here's a plot of potential energy for a collision of a proton with CO. So what we do is we have this potential energy surface in multiple dimensions, and then diagonalizing some sort of basis, the basis of the colliding particles. And so in this case, it could be CO. And then we get a bunch of these curves. Each of those curves is a channel. Okay. So those are where channels are. And say we define some total energy for our system here, about 2 eV. And we may specify that this lowest state here, so CO equals 0, is our initial state. So that's the initial kinetic energy of our colliders. And we have to transition to say V equals 3. Right, so that changes kinetic energy. Okay. So what we want to do in the calculation is consider only those states that are close in energy, the initial state, and to the energy, the kinetic energy. So that's what we mean by close. Really are many more states up here. We don't need to consider them. Okay. Okay. And we can divide this set of coupled channels into what are called open channels. So all those energies, all those states that can be accessed by conservation of energy, those up here we cannot get to. Doesn't satisfy conservation energy. But they're usually really important to include in the calculation. You still get there by virtual transitions. Okay. So those are closed channels. All right, so hopefully that set the stage for the topics we need. Okay, so let's look at an example of a collision of two diatoms. You think this problem was been solved decades ago. Right, CO with H2. Okay, one thing is, though, our initial CO is vibrationally excited. Everybody else is in the ground state. So we're looking at vibrational quenching. So there's a diatom-diatom problem. 4 atoms means 6-dimensional potential surface. Relatively straightforward to calculate the surface. Okay. However, the scattering is not so straightforward. Up until, I'm going to show you now, the largest systems that have been done in full dimension, so I got to emphasize, we try to do things in full dimension and also exact, as close to exact as possible. We remove all approximations. Okay. So before this, H2H2 was the largest system done. Seems surprising, right? But that was done only just a couple of years ago. Okay. But now we're going to do COH2. So we went out and calculated the surface. The standard method using MolPro, okay, can be done, set up a grid, run. In fact, turns out the quantum chemists involved got kind of carried away, calculated 400,000 points. Probably a record for any surface. And then we fit the surface, and this just shows some surface plots in the cuts. And we think the surface is reasonably accurate. And so given that surface, then we solve the time-independent Schrödinger equation to compute the cross-section. Okay. So here's a plot of cross-section. So 10 to the minus 16 centimeters squared, same as angstrom squared. Okay. It's a function of collision energy. Previously, there were 3 other calculations dating back to 85. But they did reduced dimensional, 4-dimensional surface, and made various kinds of approximations. So our approach is in 6 dimensions, makes no approximations. And you see previously there was a factor of 2 orders of magnitude discrepancy between calculations. Okay, so we go in with 6 dimensions, and here's our calculation. Well, there's 2 curves because H2 has a para and an ortho. Think of them as completely separate species. They don't intermix. Can't make transitions from para to ortho. Okay? And so here's our result. There's no experiment for the cross-section. But this is the first calculation done for this large of a system that we know of. Okay, but there are measurements for the rate coefficient. So the rate coefficient is where you take a Maxwellian average over the cross-section. And these measurements performed in Oxford Physical Chemistry Laboratory for a period of about 20 years, summarized in paper 1993. So those are the symbols here. So rate coefficient versus here temperature. Okay. Okay. So you can see we get pretty good agreement. Our curves are in red. Previous calculations are in blue. We have pretty good agreement with the experiment. But what I really want you to take home from this slide is to perform this calculation, we needed 10,000 channels. Okay. And really we needed more. But that was all we could fit on the computer cluster that we had. Right, so 10,000 channels. We think also as a record for this type of calculation. Okay. And it took, for these 2 little red curves, 34,000 CPU hours to do it. Okay, those 2 little curves. That's not too much of a problem. The problem really was the memory. So you might think about, all right, if I'm going to do a calculation on a teraflop or a petaflop machine, I'm also moving back and forth, terabytes and terabytes. Got to move this data back and forth. I got to store it. So that was our main impediment was storing this terabytes of data. The computing center was getting mad at us for filling up the disk. Okay. So that's the largest calculation done for diatom-diatom collisions. Inelastic, time independent. Nobody's done anything bigger. Okay. So I'm making certain approximations. Okay. By the way, stop me if you have any questions. Okay. So let's kind of step back to a little bit simpler case. And the reason we look at this case is more random. I just chose this from systems that I've done, but it's something we think we could do on a quantum computer. And we just look at the excitation of sodium with helium. It's kind of interesting that also sodium, because here it's SETI, and sodium was the first element detected in extrasolar planet, which motivated our original study of this system. Okay, so in this case, we're doing excitation from the ground state 3s to the 3p. And this system only requires, in this model, 3 channels, not 10,000, but 3. Okay. And so over here, I show the potential energy curves as a function of r, so it's one dimension. And each of these curves are the ground state, and those were 2 excited states. And so those are our channels. And over this bottom plot here are the couplings between. Now, I've got to mention, so for most scattering problems, we have dense matrices. They're not sparse. Okay. So that's an issue. Okay, so in this case, we're going to solve Schrödinger equation time dependent using the semi-classical approach. And here I'm just going to show you an example for velocity of 1 atomic units and 1 impact parameter, right? And so here's a solution for this time-dependent Schrödinger equation. Okay, and it turns out also we're going to take a straight line trajectory. So the Hamiltonian just reduces to the potential. There's no kinetic energy term. And you could choose various kind of propagators to do this. So here's this propagator we chose. Right, so here's the initial wave function at infinity, and we just propagate that with this operator. Relatively straightforward. And so what we get out are the probabilities versus the collision time. And what we want out is probability, at infinity. We have that, and we calculate the cross section. Okay. And so what we do is then we repeat the calculation for various impact parameters. It gives us this plot of probability versus impact parameter. And then we integrate over that to get the cross section. Those are the steps. Then repeat again for other kinetic energies or velocities. Okay. So then once we do that, we can get the plot of a cross section. So here's the cross section versus kinetic energy in KeV range, shown here. Only with this 3-channel model. And here's a comparison to an experiment. We're about a factor 2 larger. This experiment was done 40 years ago. Now, I might mention it's very difficult to do absolute value measurements of cross sections. Probably should be revisited. But factor 2, we're okay. It's okay for us. We do get the peak in the cross section. About right. Okay. Oh, I should mention all previous calculations, same approach, also get a factor 2 larger. Okay. So one thing you might question is, well, my basis set is too small. I only have 3 channels. Let's put in a few more channels. So I've gone up to 10 just over the weekend. Here I show 5, shown in green, roughly the same. It doesn't get smaller with more channels. So I think that the cross section is converged. Okay. So I think this is a reasonable result. And possibly in this case, only 3 channels could be used to test collision approach on a quantum computer. Okay. So let's see how we would do that. So I don't have much time to go over all the details. I'll try to show you briefly how it would work, or how we envision it work. Okay, so the single excitation subspace method, let me just mention briefly. So we have 2 to the n size of the Hilbert space in a quantum computer. But in this approach, we don't use all that. We just use the n dimension of this, called at the single excitation. Okay. And we'll see that for each qubit corresponds to a channel. So every channel we have in our collision problem, we need a qubit. The beauty, or the advantage of this method is, then we have control over each element in the potential. All n times n plus 1 over 2. The diagonal, and all the off diagonals. Of course, the Hamiltonian, the potential is diagonal and real. Right? So just upper half. So we have control over that, to whatever experimental precision there is. The other thing is, 2 things. We can run it within the coherence time or even earlier. Right? You can run for shorter and be done. And then the method does not scale with them. It's independent of that. So it takes the same time to do a 10-channel calculation if I had, or 10,000 if I had 10,000 qubits. Same time. Okay. So those are the advantages of the method. Some issues, as I mentioned, every channel we need a qubit. Some people also complain, maybe we also need this classical, the computed potential matrix. But I would say that's relatively straightforward, we can do that. Today, 10 atom potentials can be calculated. So 10 atoms, which is how many dimensions? 24. Dimensional potentials, okay, straight, can be calculated. Okay. And there's some other issues I'll get to in a minute. Okay, one other issue, though, is we do need a fully connected quantum computer. Every element, every qubit has to be connected through a variable coupler. Okay, that's the one problem there. Okay. So what's the process? The process is we have our pre-computed potential diagonalized in some basis, okay, with diagonal and off-diagonal elements. What we do is we match that to the quantum computer Hamiltonian, directly map it to it. Okay. There are different energy scales I mentioned in the beginning. So energy scale of the, for example, superconducting qubits. So we have to scale to get the right energy scale. This parameter lambda. Turns out that's really beneficial, though, that there was this parameter. We'll see. And so when we do this offline, we end up getting a set of off-diagonal elements for the quantum computer as a function of some quantum computing time, and the couplers also as a function of quantum computing time. And then that's sent to the quantum simulator. The simulation is run, record the counts, do it again. Okay, and all these methods are described in this paper by Emily and Mike, which you can get on the archive, these steps. Yes?
If you got a full-blown quantum computer, then why not just use a simulation method like Zolkin's method, the potential surfaces, to directly calculate scattering?
Well, I'm not a quantum computer. I'm not sure familiar with that method. Maybe we talk about that later. Okay.
But this doesn't require the perfect quantum.
Right, that's right. Doesn't require that. It requires the qubits that are available today you could use, if you could put them together. Okay, so here's just a typical example of what we get. Okay, so again, we calculate the probabilities, but now as a function of quantum computing time, we just run the quantum computer, and then at the end, get the probabilities. One shot. Okay, here, less than 100 nanoseconds. Okay, and this can directly be mapped to what we got on the classical computer here. Notice that there's different in the shape. That's because we can design the scale parameter lambda, so if you spend more of the time where there's an interaction in the quantum computer. Okay, physically, not much happens until the particles get close to each other and they go apart. So we can stretch that out in the quantum computer. But really all we're interested in is the probabilities at the end. However, there's an interesting thing. If I do a real collision experiment, I send in some particle beams and I put a detector out there, one can measure at the end. On a quantum computer, I could stop the simulation at some intermediate time and see what's going on. Okay. So there's some almost like it's very similar to a regular calculation on a classical computer. All right. So that's basically the steps. You repeat, as I showed before, different trajectories, different velocities to build up cross sections. Okay. Well, of course, we have to talk about there's some caveat to this approach. Okay. And so the first problem is on a classical computer, at the end of the trajectory, we get probability. Because we propagate scattered amplitudes. On the quantum computer, you get a count. And so we have to rerun again and again to build up probabilities for each of the channels. Okay. So we have to repeat this some n number of times. And so I just took an example of the sodium helium problem. I extended it to 10 channels, and I knew what the probabilities were. And I just asked the question, okay, in the weakest channel, if I want to get, say, 10 counts, which really would be something reasonable, 10 counts, so I can measure that cross-section. Well, how many counts do I need to simulate the whole thing? And so in this case, I get a little over 700 runs are needed to get that weakest channel resolved to 10. So you see it's kind of scaling like n cubed for the number of runs I need to do. Of course, that's if I want to know all the details about these unimportant channels. You can imagine I could stop much earlier if I just wanted to know the cross sections, the dominant channels. So then it's up to you and how accurate you want to get the probabilities. So maybe it could n squared is enough runs. Okay. Okay. So that's one problem with the implementation. Another problem is with the method itself, from even on a classical computer. And that is that the assumption is that the kinetic energy, the total energy, is actually way up here above my set of coupled channels, okay, for a straight line trajectory. So the trajectory doesn't know anything about the potential for it to be a straight line. And so it means kinetic energy must be much larger than any energy gap between internal states for the method to work. Okay. Where del T is that difference. Okay. Well, you can imagine I can improve that by calculating a curvilinear trajectory, but then the question comes about, what curve do I use? Because then my trajectory starts to see all those individual channels. Okay. So that's a problem, and it was recognized in the quantum dynamics community. So roughly in the 70s, it kind of abandoned this approach. It went right to the wave packet method. Okay. However, it's still used in atomic collisions because more interested in higher energies, KEV. So it was okay there, but chemists were more interested in room temperature. So that was a problem. Okay. So you can imagine as I go to even lower energy, chemical regime, that's where the problem occurs. Okay, well, and so this I really learned recently by exploring the literature that actually the chemists have revisited the problem. And that just in the 1990s, Billing, so-called, why can't we mix certain quantum and classical effects to come up with what they call now mixed quantum classical theory, which is really the same as semi-classical scattering theory. Okay. And what he proposed, and he has a long textbook of how to do this, but the bottom line is we can just take an average over all the kinetic energies, okay, and to get a kind of average kinetic energy. It turns out as long as that average kinetic energy is greater than the smallest change in internal states divided by 4, gives you an explanation of how this works, that you can do the semi-classical approach. The answer because this symmetrized Ehrenfest approach. And just recently, it was tested, just this year, and for a collision of helium with water. Okay. And just look at rotational quenching. So here's the cross-section versus kinetic energy. The red curve is actually our calculation for my group, time independent. So of all these resonances. Okay. And so I'll refer you to the energy here. So that one wave number, over here, 10 to the 4 wave number is 1 eV. This is really low energy for this method. Without doing this Ehrenfest averaging, here's the result that this group got, 5 enough. So it doesn't look too well, factor of 2 or 3 off, but they apply this Ehrenfest approach, it's much closer. They don't get the resonances, but at least the magnitude is pretty close to the full quantum calculation. So this gives me some hope that the SES approach could be applied to relatively low energies. Okay, so that's my last slide. So, so in our group, we're going up to larger and larger systems. The sodium helium case, I could run here on my Mac Air, no problem. 10, 100 channels. Okay. If we want to do diatom collisions, we really need hundreds of cores to do it. Okay. So here's our cluster at UGA. We can do it on. I mean, what is the cluster we ran our COH2 stuff on? What we basically saturated. Okay. If I want to do many more, or by the way, the rotational angular momentum, the CO was set to be 0. If I want to go higher, the problem gets even larger because the number of channels goes as j squared. Right, sorry, 2j plus 1. Right. So there's this degeneracy, and the channels grow quickly. Okay. And so we really need to go. This for that COH2 problem. We need to use the petaflower sheets. So that's our next goal. Well, so from there to there is some opportunity now to look at, find the SES method on a quantum computer. Okay, so just to summarize, exact scattering calculations for inelastic collisions I discussed today and also reactive collisions, let's say, lags behind development in quantum chemistry. Probably because there's a lot more money in quantum chemistry than collisions. Okay. We are engaged in developing algorithms so we can do faster, bigger systems, but it's in progress. What can we do in a quantum computer or quantum simulation? Right. So there are potentially some problems which are feasible today. It can be done in classical computers. Okay. Some kind of systems which are really dreams for us, classical or quantum. H2 planet water cannot be done today on classical computers. Even Titan cannot do this problem yet. Wow. Okay. Partly because algorithms aren't developed, but I think no one's tried it yet. Potential is only 90. And this other one is really important for studying protoplanetary disks, methanol, and H2. Nobody's even thinking about doing it. Okay. So those would be some really target systems we like to do, and even some ones important in atmospheric chemistry, because these molecules are really heavy. Number, a couple channels grows dramatically. Okay, I think that's all I have to say. Okay, and I'll leave you just with this one little plot which shows what can be done with reactive scattering, which I didn't discuss today. They can do maybe up to 6 atoms, but there's a whole range up here. More only can be done with solving Newton's equations. Cannot be solved time or time independent Schrodinger equation. Okay, thank you.
So I have 2 questions.
Yeah.
How many qubits would I need before I could actually tell you something that you couldn't tell me? And in that case, could I still calculate the scaling parameter lambda easily, or would that become a challenge?
It's calculating lambda is no problem. Yeah, it's totally straightforward. It doesn't matter how the number of channels. That's not good. Okay, so this is a good question. Mike and I discussed this some today, this morning. So for a time-independent problem, Mike has looked at something like a few hundred channels, a few hundred qubits, maybe something like 100 or so qubits for a time-dependent problem, a scattering problem would be interesting. Not that we couldn't do it on a classical computer, but could be competitive with a classical computer. Maybe 100 channels. A few hundred, maybe less. Depends on the problem. So that's, but we haven't gone through the full analysis of that yet. That's speculation. It's maybe reason. It'd be something interesting to try.
As time dependent.
Time dependent, right.
Which would require 100 by 100 connections
Yeah, fully connected.
and control.
That's right. Maybe but 10 may be interesting.
Yeah,
but
10 or, yeah, right, I understand.
Yeah.
Yeah.
So to do something really interesting, like methanol plus oxygen, how many qubits would that require?
Okay. Well, it depends on the question. Okay. If you want to solve the full vibrational motion of, methanol, the whole thing, no approximations, yeah. Okay. I can't tell you the number.
Well, I'm ballparking at around 4,000 or 5,000.
Yeah. Let's see if I can find. I do have a way to estimate it here somewhere.
Okay.
Okay, so I just tried to did show. Oh, no. Let's see if I can find that one. Okay. How is it going to build? Sorry. Here we go. So here's a way to estimate the number of channels, roughly. So 3 times the number of atoms minus 6, right? So how many atoms are in methanol? I think it was a 12-dimensional problem, right? So that's 12.
And methanol is 6, oxygen, so it's 8 atoms.
Okay.
Why is minus 6? Because you pick up the
Center of mass,
motions.
the center of mass motion, and it's in the frame of the molecule. So you remove
Okay.
also the 3 Euler angles.
It's just symmetry.
Right. And then
So
the number of vibrational states you need in the basis, number of rotational states, and then if this would be 1 if there's no reactive process.
Well, we love our reactive process.
Yeah.
So there's a lot of vibrational modes and a lot of rotation, and you're going to get a big number here.
Yeah, it's going to be.
Okay. So yeah, ballparking it in the single-digit thousands is probably
I think,
right.
yeah.
Yeah. Okay. And then they would need to be fully interconnected.
That's right. Well, okay, so if oxygen, you mean neutral oxygen, atomic oxygen or molecular oxygen?
Molecular.
Molecular, okay. So then you also have the basis of the O2 as well to be included.
Well, the system CO plus H was studied extensively back in the 70s and early 80s as part of the synthetic fuel effort. So, I mean, I remember that, and this is obviously much more better. Any kind of combustion chemistry, there's a lot of interest in that. So, you would need several thousand plus to do systems like methane plus oxygen would be similar.
That's part right, yeah.
Yeah.
We've done COH recently.
Okay.
More detail.
Right.
Okay, so really billions went to include error correction.
No, you don't need error
Don't need
correction.
error correction.
The entire
There's no-
algorithm is independent of the number of qubits and a number of channels, and it can be done in under 100 nanoseconds.
You're not going to get fully connected.
That's the
That's
only
another
experimental challenge, but it is all DC control. There's no microwaves, which makes it experimentally.
Sure,
But I agree, fully connected is fine.
as soon as you can't do fully connected, you have to
No, then you're done.
lights and
And then
do
you're
error correction. So yeah.
It's clearly there's room for improvement in the technology.
Maybe
Current
motivate.
targets are, billions and tens of millions of qubits. We work to improve that.
Okay, so let's stop there. Next, Rami Barends is going to be talking about design of a superconducting quantum.
We'll just keep spending money on this stuff.
On what?
CO plus H.
This is an Apple thing or something?
Yeah, you want to take that on.
Okay. Is that okay?
I really
This
do
is-
that.
I
We really want it.
Yeah.
This is good.
It's in it. But I think maybe, yeah, let's do that. It's just.
All right. We recently had a great result at least in Santa Barbara. We have devices which are not very precise, which have a performance which is at the level required for fault-tolerant quantum computing. My name is Rami Barends. This work was done together with Julian Kelly, as well as a whole group of authors who work on materials, on amplifiers, on readout, pretty much all the elements you need to scale up to large quantum systems. Now, you probably think, well, I signed up for some quantum simulation conference, and here's some dude talking about, error correction. What the heck is this? But what I want to tell you is that in both quantum error correction and in quantum simulation, if your algorithm is composed of gates, then any success depends critically, or is defined even by the fidelity of those gates. And this is where these two things overlap. So you need to work with those gates. Qubits are faulty. Qubits interact with the environment, which leads to accumulation of rotation errors, or even to energy loss or loss of phase coherence. And if you want to scale up larger systems, you want to have some form of error correction. Now, the surface code architecture is one way to implement a fault-tolerant quantum computer. And the simple way of explaining this is that you put in that architecture, the qubits are placed in a checkerboard pattern with data qubits on the white squares, measure qubits on the dark squares. You only need nearest neighbor coupling, and the measure qubits detect errors in a rapidly cycled entangling scheme using single and two qubit gates as well as measurement. Now, this whole thing starts to run only when the gate fidelity, the fidelity of your logic gates is good enough. and that threshold is around 99%. And once you have that working, you know, the measured qubits give you data, you know, ones and zeros, it's classical, and from that you can piece together what went wrong, which of the qubits had a bit flip or a phase flip, or, you know, more intricate error mechanisms. Now again, this whole thing starts to work only when the errors are below a certain threshold. Only then will you get an exponential suppression of the logical error rate with an increasing system size. We became aware of the surface code architecture 2 years ago through our collaboration with Austin Fowler, who is now at UC Santa Barbara, and he's sitting right over there. This year, we actually got this result where we have quantum circuits which are at, you know, which have a performance which is at this threshold. Now, I already talked a little bit about the surface code and fault tolerance. The key to this whole approach is superconducting quantum circuits. Now, superconductivity is something, you know, maybe you know. Most people, you know, in the street or, you know, would know it from MRI machines, particle accelerators, magnetic levitation, whether it's for transport or lifting, you know, heavyweight champions. What we use it for is because superconductivity has a unique feature, namely that the conduction electrons condense into a macroscopic quantum state, a single macroscopic quantum state. So what you can have is have one superconducting island, another superconducting island, two phases, phase left and phase right, and connect them using a weak link. And what you'll get through that weak link is a supercurrent, a current which will flow without any dissipation and depends non-linearly on the quantum property. The smaller the link, the larger the inductance. So we have, if we have our inductance here and place a capacitor, we have a quantum circuit. Now, this is how it looks like. Any superconducting qubit you will see you know, in the literature is a variation of this theme. A Josephson junction, the weak link, and a capacitor. Now, the energy of the system is defined by two parameters, the charge and the phase. So it basically depends on two axes, if you will. The qubits we are using are based on the transmon. It is frequency tunable, so we change out a single junction with a squid. This is basically a ring with two junctions, and it becomes effectively a tunable junction. This way we can tune the frequency. In addition, we choose the charging energy much smaller than the energy associated with the junction, so we're in the limit that the charging is much smaller. Effectively, the Hamiltonian no longer depends on like two axes, but it's pretty much only one-dimensional. So your quantum state, if you like, lives inside the cosine potential well defined on the coordinate phase. Now, we went, this is an optical picture of the qubit we're using. As said, you know, it consists of a inductance formed by a squid ring and a capacitor. And the capacitor here is cross-shaped. And it is cross-shaped to allow for easy coupling, but also for microwave hygiene. I mean, what you want with this qubit is when you need coupling, you want it, and when you don't want coupling, it needs to be isolated. And this design is very clean in microwaves. You know, if you know a little about microwave engineering, this is a coplanar line which naturally comes with very, very little, you know, radiation, you know, at large distances. Maybe it's easy to explain in the following way, with the center of mass argument. The center of this cross is here, so kind of the center of where most capacitance or most of the charge is around here. So you can come up to it and connect to one arm, whether it's for readout or for interacting with another qubit or for control. But if you're far away from it, you're quite far from that center of mass. So it allows for coupling when you want it, and otherwise it's isolation. So this XMON design, you know, combines connectivity, control, as well as coherence. And you know, getting this combination is something which has, I think, eluded the field for quite some time. Now, we've gone through quite an optimization track when we started in 2012. You know, we started and you know, working on materials, working on this design, working on you know making sure the qubit environment is quiet, These all contributed to basically going from a T1, an energy decay time of a microsecond, to over 50 microseconds, almost 2 orders of magnitude increase in a little over a year. So this is like almost an unparalleled track, I think, in our field. Now, 50 microseconds, what does that mean? What you have to consider is that the gate times, both single and 2-qubit gates, are between 10 and 40 nanoseconds. So with 50 microseconds, we are over 3 orders of magnitude from the gate times. So that's really the range you want to be at to start thinking about fault-tolerant thresholds. Let's go back. I already explained this graph. Surface code architecture, nearest neighbor coupling, single and 2-qubit gates. That's all good. What we ask ourselves is, can logic gates be good in an architecture which is compatible with, or first step towards the surface code? So we built this chip. It's a 5-qubit chip, so 5 of these cross-checked qubits are on a row, Q0 to Q4. Each qubit has individual control, X, Y, as well as Z control. Qubits have individual readout, and the readout is multiplex. So each qubit can be individually addressed, individually read out, yet all done simultaneously. 2-qubit interaction is then done by tuning the frequency. If you have dissimilar frequencies, they're effectively off, and when you want them to interact, we bring them close together in frequency and pull it back up to turn it off. So we have controllable 2-qubit interaction by tuning the frequency, and this is something that IHRs cannot do. And again, surface code architecture calls for a 2-dimensional grid. It's a surface. The experiment we're doing here is really we take a strip out of that plaquette and put it on a chip. It really is a linear version just to check whether the architecture works, whether the gates work, etc. Devices work. We find that energy coherence times are consistent between 50 and 40 microseconds. Some shooters do like up to 60 microseconds, I said you that before. But the energy coherence time here is consistent across frequency and across qubits, and this is really what you want. So, okay, good. We have a device works, energy coherence times is good, let's move towards gates. One way to, or the most used way, I think, up to now to quantify whether a gate or a quantum process works, or to benchmark that, is using process tomography, quantum process tomography. And what you do is you input a complete set of input states, you measure the output density matrices, and try to pull out what the process matrix is. The problem is that that tool depends or is negatively affected by initialization errors, measurement errors, and in fact what these things do is that they mask what actually is going on. They map onto the process matrix in a way which is non-trivial, and actually, there's no use, and they mask what is going on. So process tomography looks great on paper, but in practice it's not really what we want to use. Instead, we use randomized benchmarking. And in randomized benchmarking, you test the gate, as said, in a sequence of random gates. So let's start. So we have a random gate, another random gate, another random gate, and random gates, and we append a final gate which inverts the whole sequence, such that the unitary of the whole sequence is identity. So nothing should have happened. So if you start in the ground state, you should also end in the ground state. So if you measure the ground state population versus sequence length, you see it decreasing, and this decrease is due to the accumulation of gate errors. Let's call this the reference. Then what you do is you take random gate and interleave a specific gate, random gate, specific gate, and you see a decrease in the sequence fidelity. And this decrease is basically tells you what the error is of that specific interleaved gate. That's how it is. You just fit an exponential. Now, those random gates, they're not just random gates, they have to be specific random gates. And what we use for that is the Clifford Groups, Clifford gates. The Clifford Group is a group of rotations which, in the blocks representation, preserves the octahedron in block space. It is a unitary 3 design. For benchmarking, you need a unitary 2 design, so this will do the job pretty well. If you don't follow, that's fine. The intuitive picture is
you rotate the state around the block vector such to get a properly averaged estimate of your gate error. And this is how we produce the different notations. So let's start benchmarking. We start with a reference. Yes?
So why do you need a finite group? Can't you do some dense group of the unitary, or maybe?
Why would you?
Why don't you use some dense group in the matrices, in the unitary matrices?
You don't need to. So what you want is you want to have the okay. So you don't need to. What you want is to have that these random gates are short and easily implemented, and this is something we can do with on typical 1.8 physical gates for Clifford. And for gate error, because gate error depends quadratically on, for example, over and under rotation, you only need a unitary 2 design. So you can go for denser groups, but it's not going to give you a bad answer. So you want to be as efficient as possible, and the Clifford Group does that for you. So let's start benchmarking. Let's start with a reference and then interleave all kinds of gates. We leave, pi rotations, pi over 2 rotations. I give a pi over 4 rotations. On the x-axis, y-axis is, for example, a minus pi rotation around the y-axis. A Hadamard gate, the T gate, we have to do 2 because it is outside of the Clifford group. And what you see is that all the single qubit gates have a fidelity of 3/9 of the error. Gate errors for single qubits is below 10 minus 3. And this is a record for superconducting systems. I haven't seen this anywhere else for superconducting qubits. But the trick is not to show this for 1 qubit, but for this, and this one, and just generate this whole table. Lots of numbers. It's okay. I want to focus your attention on this line, the average over gates. And what you see is that the average over gates for each qubit is very similar. We have consistent high performance of the whole chip with an average over gates over qubits of 3/9. This is what you want. If you want to scale up, you want to have proper, you want to be able to maintain fidelity in a consistent way. Okay, so single qubit gates work, but you know that doesn't bring you far. You need an attaining gate, and for that we use a controlled phase gate. And the way we implement it is by the qubits are in the off position. They have dissimilar frequency. We put the qubit on a trajectory which brings it close by to bring about a conditional phase shift and pull it back. That's how we implement it. And if you go too fast or the trajectory is wrong, you end up putting population in the higher levels, which is something you don't want to do. That is non-adiabatic leakage. That's not what you want to have. You want to go nicely, smooth, come back again. And doing that properly is actually quite challenging. Now, let me try to explain this to you. So we have 2 levels, the 1-1 level, the 0-2 level. That's something you can actually present in a block 3 representation. So suppose we start in the 1-1 state, and we put the control vector just on, then it will, the state will preset around this control vector, and then we have to turn it off exactly. And what you will end up with, if you do it right, you end up in the 1-1 state, and there's a phase shift because it rotates. The problem with that gate is you have to turn off the interaction immediately. So your controlled shape looks like a square wave. Now square waves work wonderfully well on paper. They work well in the computer. In the lab, to generate a square wave, because of the whole frequency spectrum, is not possible. So this gate is hard, and it's only single optimum, right? If you rotate too much, it's always error. Instead, Mike Geller and John Martinez came up with another method. What you do is you move adiabatically. So you take a control vector, you put it in a 1-1 state, and then move first fast and then slow, and make sure that the state vector will follow your control vector, and then move it fast back. And that can be translated into spectral window theory. And what you come up with is something which is almost as fast. This is 1.2 times the effective time constant or speed of the system, and it has an error of like 10 minus 4, 10 minus 5. And anything above this is optimal. Okay. In practice, decoherence will kick in, but this is something you can tune up. And if you look at the pull shot, this is smooth, this is round, this is something you can build. So this is something we're going to use. Now, to benchmark that, we need Cliffords not for a single qubit, but for 2 qubits. This is the cookbook, which the guys at IBM published on how to construct this 2-qubit Clifford group and to get a properly averaged estimate of the gate error. And we just supplant C-knobs and swaps and I-swaps with CZs. What you start to see here is this is starting to become pretty complex. You know, this thing over here has three 2-qubit entanglement gates and a bunch of single qubit gates. This is starting to become an algorithm. This is hard. And you know, this is how it looks on the computer screen. This is an MS3 Clifford sequence. So it consists of 3 Cliffords and a final gate, which makes the whole sequence the identity. And there's lots of gates. You know, all these wiggles are single qubit gates. The red pulses, you know, that puts, you know, qubit A on a trajectory, which, you know, implements the control phase gates on the other one, both of them. Yeah, this is pretty complex. And again, the whole unitary of this, well, almost circus, I call it, is identity. This is how it looks on the computer screen. Let's go to the lab. So when samples are mounted at the bottom of a 20 millikelvin fridge, they're inside a magnetic shield. Lots of wiring. This is where we have to filtering, you know, infrared light, infrared filters, you know, high frequencies, you know, bleed through from local oscillators, etc. Lots of filtering. These cables all go outside. They go up to room temperature, come out here, and here they go into control boards. Each level or each drawer is pretty much a control board. And here's a scope which we use to monitor what the output is on that control board. And this is a picture of when we're doing benchmarking. And what you see is, you know, in yellow, single qubit pulses on qubit A or qubit 0. Blue, single qubit rotations, you know, your pi and pi over 2 rotation around the x and y axis, and actually also z axis, that's implemented with x and y on the qubit 1. Green, the pulses which bring the qubits along the frequency trajectory. And red, actually, you see the crosstalk correction in qubit 1. But the crosstalk we have is like 1% or below, so you can't even like see it with the naked eye on this scope. Now again, we're sending up to 800, 900 single and 2-qubit gates here. We generate that, we send it down the lines, you know, we generate on the board, send it down the cables, send it down the fridge, onto this like cold stage, into the sample, into the lines, and such that the qubits like, you know, follow that dance and interact and do everything. That we measure, and we basically see, you know, we measure the probability of the ground state, and we see this exponential decay. And the end of this whole complex sequence, we just treat an exponential. I found that amazing. And you can just do this. Yeah. And here's the results for the 2-qubit gate. So we start with the reference, yeah, 2-qubit Cliffords, and then we interleave the control phase gate, and the difference will give us an error, and the fidelity of this gate is 99.4%. And when we do this for all the pairs, we have 5 qubits, so we have 4 pairs. We see 2-qubit gates fidelities between 99.0 and 99.4%. Again, the fidelity of these gates is very consistent, very similar across the whole chip. And this is really what you want. When you want to scale to larger systems, you don't want the fidelity to start to nose down. Yeah, you want to have good fidelity. So, we are very excited about this one. And actually, our numbers compare very well with what has been published in the literature. Now, 99.4%, that's actually like on par with what has been shown by ion traps, and I believe this number is now even higher. Mind you, this was done in a 2-qubit system, whereas our chip is a 5-qubit system. So if you go and compare with a larger scale system, a 5-qubit ion trap, even this year, yeah, it's I think a few months ago, they had 95% fidelity on a 2-qubit gate. And it's not because they're not trying, it's because it's so hard. It is so hard to do this. And to control a single qubit or a group of 2 qubits in a whole sea of other qubits. Superconductivity, because of the macroscopic phase, because of the physics, because of the compatibility with microlithography, naturally allows for this. It naturally allows you to build a quantum integrated circuits where you have addressability and you can scale up. That's something you really want. Well, so far we've looked at single 2-qubit gates. 2-qubit Clifford benchmarking is quite an algorithm. So you can actually start to think about making an algorithm with these gates. And the simplest algorithm we could think of at the time is let's generate an entangled state. Now you can start with a Bell state or an EPR state, I believe. Wire for 2 gate on the first qubit and then the CNOT on the second. All right? You can put in another one, another CNOT or a fourth one with another CNOT. And you see that this algorithm is actually quite modular. Or heck, you can even bring the fifth one with another CNOT. And you see that the fidelities are very reasonable for considering the amount of qubits, the amount of Hilbert space you're having. So we're testing here a modular algorithm on a chip which has a modular architecture, and things work. And that's it's very it's something which I find great. And for this 5-qubit state, all qubits, all control lines, all resonators, everything, every element of the qubit is operating simultaneously in generating and in constructing and in characterizing the state. And this is the largest direct tomographic measurement in solid state today. Okay, so good. Single qubit gates work, 2-qubit gates work. An algorithm consisting of 5-qubit gates work. Let's start thinking a little bit more further. And this is ongoing work with Laura García-Álvarez, Lucas Lamata, and Enrique Solano. And they come up with the idea of simulating the Hubbard model. And this is the Hubbard model for n fermions. For 2 spins, it can be rewritten like this. And what you see here is this XX, YY, and ZZ interaction. Single qubit gates, of course, and single qubit sigma Z gates, which we actually can even do virtually. You don't even need to send down a pulse. If you want to simulate this, the time evolution, you can write the Trotter step. And what you see in this Trotter step is there are 3 elements: this X, X, Y, Y, and ZZ, and so say qubit phases. But what you see is there is a sigma Z operator, which is a 2-qubit gate effectively, and single qubit pulses. And this 2-qubit gate consists of itself of 5 pulses and a controlled phase gate. Well, we just did controlled phase gate. Good. Let's see how this works. So the nice thing about this benchmarking is that we can chop up this algorithm, look at the individual elements, and start to quantify that. And let's just do that, So that's the benchmarking with these steps. Again, let's start with the reference, just 2-qubit Cliffords, and let's interleave the sigma Z gate here for a phase such that it fits within the Clifford group. And what we see is a gate fidelity for this gate, for this parameter of 2.4%. So it's effectively 1% per CC phi gate and a few pi pulses, so it's very reasonable. Okay, well, that seems to be reasonable. Let's put in the whole Trotter step. 3 of these, and say a bunch of single qubit pi pulses, and we get an 8.5 or 8.6% error. And this is actually very reasonable, considering it's 3 times this guy, so 3 times 2.5, it's around 7. 10 times gates which have fidelity, an error of 10 minus 3. So that's kind of like 8%. So what you see here is that the algorithm is modular, but you see that the errors associated with this algorithm is also something which is modular. You can basically add errors in this way. It adds consistently. So you can generate an error model and actually optimize for lowest error with these algorithms. So this is, I think, really great. And we're doing this on a 9-qubit chip now. So this is something we also want to do error correction experiments on. So I guess, Joe, what did you say? We need to double every year?
That's your task.
So we're trying. It's not 10, but okay.
Okay, it's close enough.
Yeah, excellent. Good. So to summarize, all this work into getting the environment of the qubit good, getting all this work on gate design, all this work on coming up with a qubit, which is an essential building block of the whole architecture. That all comes together in constructing this 5-qubit quantum integrated circuit, where we have demonstrated single 2-qubit gates with a performance which is at the levels required for the surface code fault-tolerant quantum computing. And heck, we also put in a 5-qubit entangled state, which is the largest tomographic reconstruction so far. But all this was all just a warm-up. I mean, we now know that the architecture works. And what we can, for the first time, really start doing, not just think about, but start doing, is implementing simulation and error correction in large-scale quantum circuits.
classical coding theory, the algebraic symmetric codes are written eventually by random codes like turbo codes and LGBCs. Are we sure that this will not happen in quantum computing eventually?
You mean in error correction?
Yeah.
I think Olsen is a better person to answer your question there.
What makes you hopeful that LDBC codes are better? What makes you hopeful?
I think our phones are working.
An LDBC code requires long-range interactions. So one, that's already hard to build. Lower threshold error rate, harder to build. Classical algorithms code the common case are not known to be efficient. They have a lot of restrictions. People don't know how to solve full problems in a polynomial manner. So, secondly, it's a quantum memory. It's a quantum computation. You have to teleport the data out of the code to compute. And then when you're going to use compute, you use surface code. So the overhead in terms of space-time volume is actually strictly greater when you use an LDBC code. The only thing you gain, if you have long-range interactions, very low error rates, and solve the classical problem of decoding, is the potential for fewer qubits. But it's going to take you an awful lot longer to compute anything because you're going to uncompress and recompress all the time. So they're not practical because quantum computing is slow. Even a fast superconducting app is only 10 or 20 megahertz computer. You can't afford to throw away time to save space. You have to optimize the time. It means lots of qubits. It's the only way you get anything done. So at the moment, I see no theoretical hope for it.
So these things are what, 50 or 100 microns across?
The qubits?
Yeah.
Yeah, 200.
200 mics. So right now with current chip technology, you could probably build one of these things with a few dozen of these qubits, individually addressable random access.
No. You should be able to do more. Look, the architecture we're showing here is just linear. What you want to go through is a surface. And to do that is, the picture I showed you. For that, you need to separate out, read out and control on different layers. And what you then can do is go, to squeeze down the size of this qubit to like 100 microns or something. Well, your chip size is how much? Centimeters. So where we're talking about what, 100 by 100. So these are kind of numbers which they would fit on a chip. Now, the big thing is, how do you separate out these layers and maintain fidelity? And that's something which is, it's a big engineering challenge. And right. I think what you see a little bit is that this field is starting to become, start to understand what is necessary for those things.
Well, these first generation linear architectures have the advantage that you don't have control and readout lines on top of your qubits, potentially causing interference. So these are cleaner architectures in terms of noise.
Yes, well, if you want to build a surface, you need to do this anyway. You need to move the control lines. And the advantage of this qubit is, it's like a few hundred microns, 200 microns across, squeeze it down to 100. It's the advantage that you have actually room on the chip to come down with, a bond pad or a wire or whatever, to set, to split out do some control there. You want to have room on your chip to put in your control line and readout. So the challenge is to move readout on a different layer in a way which is still compatible with this and maintain fidelity. And that's something which this is something we will need to do to have a large surface.
Right.
A large surface.
Yeah, I wanted to emphasize that everyone thinks in the CMOS world you want to get smaller and smaller, and that's because the control circuitry for CMOS is really trivial. You have a ground bus and a supply bus, and you're done.
It's trivial.
When you do qubits, you have this analog control on every qubit, so you have to build control circuitry for that. And that requires a lot of wires or in-circuit control, whatever. So making it smaller and smaller is bad. I mean, you intuitively know that because you're not going to build a quantum computer from a molecule, because you can't get wires into each atom or photons. So we think that 100 or 200 micron size is actually a good, point where you can imagine getting into control circuitry.
Yeah, but that size is optimal because substrates are that thickness, so distances are kind of like that. It's big enough to put like
We have to see.
we have to see. But it's not a crazy size.
It's a good size.
It's a good size.
Right, and it's also consistent with the fact that somewhere around 1,000 qubits or 10,000 qubits, we start to develop interesting devices that can do things that just can't be done in a classical computer. We start to develop things that are 10 orders of magnitude faster than a classical computer. And it starts to look like a really interesting technology.
Yeah, totally. Although I don't know whether you're referring to 10,000 logical, like corrected qubits, or 10,000 physical qubits, because that's the big difference.
Net qubits.
I think, but yeah, I think if you could, with this basic technology, I'm hoping we could get up to something like 1,000 on a chip, in which case you show something interesting, and then that's motivation to solve the next problem.
Good, thanks. So lunchtime